Imagine walking into a large auditorium. You see 20 rows of seats stretching toward the back. The first row has 30 seats, the second has 32, the third has 34, and the pattern continues for every row in the section. If you need the exact total number of seats, you could walk through every row and add them up one by one, but manual addition is repetitive and prone to simple errors. Mathematics provides a specific tool for this, the arithmetic series sum formula. It allows you to find the total without summing each term individually. By identifying 3 properties of a sequence, you can determine its total value quickly, replacing minutes of repetitive addition with a single calculation. To analyze any sequence, you first need to identify 3 variables. There is the starting value, A, the constant rate of growth, known as the common difference, D, and the total number of terms, N. This diagram shows your 2 options. On the left is formula N. This is the more direct route, but it is only usable if you already know the specific value of the final term in the sequence, represented by L. If that final term is unknown, use the standard formula on the right. This version works as long as you have the starting point and the growth rate. Both equations provide the same result. Selecting the one that matches your known variables ensures you can complete the calculation in one pass. Let's apply this by finding the sum of the first 20 terms of the sequence, 3, 7, 11, 15. First, we extract our variables. Our starting term, A, is 3. Each term increases by 4, so our common difference, D, is 4. Since we are summing 20 terms, our N is 20. Because we don't explicitly have the value of the 20th term in our sequence, we will use the standard formula. We substitute these values into their corresponding positions in the equation. Following the order of operations, we simplify the innermost bracket first. We subtract 1 from our 20 terms to get 19, then multiply that by our difference of 4, resulting in 76. We then complete the work inside the main bracket. 6 plus 76 equals 82. Finally, we multiply that by our halved term count, which is 10, to reach a total of 820. Moving step by step from the inside out ensures the calculation remains accurate and easy to manage. It is important to be precise, as one misplaced value can change the final result. Consider this attempt to sum 10 terms of a sequence starting at 7 with a difference of 3. The error is in the bracket. The student used the total term count of 10 as the multiplier, rather than subtracting 1 first. This diagram shows the correction. By applying the n-1 step, we multiply the difference by 9 instead of 10, which yields the correct total. Misidentifying the multiplier is a common mistake that leads to an inflated sum, so always double-check your substitution. Now we can resolve the auditorium problem using this verified method. We inventory the physical space, a starting row of 30, an increase of 2 seats per row, and 20 total rows. We place these values into the standard formula. We simplify from the inside out. 20 minus 1 is 19, times 2 is 38. Adding the initial 60 seats gives us a total bracket value of 98. Multiplying that by our halved row count of 10 gives us exactly 980 seats in the auditorium. By organizing the physical rows into a mathematical sequence, we find the total in a fraction of the time it takes to count them manually. You now have a reliable framework to calculate the sum of any arithmetic sequence. Remember the process. Inventory your variables, choose your formula, and simplify from the inside out. To test your accuracy, try calculating the sum of the first 50 even numbers, shown here on the screen. Work through the formula on your own and compare your final total with others in the comments. Mastering this formula provides a consistent way to handle large totals, allowing you to process repetitive data with speed and precision.